class A commutation or the load commutation. So now basically we are going to learn about the commutation techniques in order to switch off the thyristor very forcefully. So I have already told you thyristor is a semi-controlled switch, means only we can on the switch but we cannot off it. So only user can on it but can't off it. So if you want to off it, then you have to go for the forceful commutation. So by using the forceful commutation, then only we can off this thyristor. So out of this, the first method we are going to discuss, which is the class A commutation or the load commutation. Let us take a small here. This circuit is going to consist of thyristor. So this is the thyristor. So this is the source voltage, which is Vs. Here I am going to take a load is having resistor, inductor and capacitor. So these three elements I am going to consider, which is the resistor, inductor and capacitor, and the current through these elements, which is I of t. So these LNC are called as the commutating elements. LNC are called as the commutating elements. So now I am going to assume that SCR is in on condition. I am going to assume that SCR is in on condition. So if I apply the Laplace transform, that is, this is the DC voltage. So therefore finally I of S is equal to Vs by S by R plus SL plus 1 by SC, which is overall supply voltage by overall impedance in the Laplace transform. So if we do a simplification, further analysis, then we are going to get Vs by L by S square plus R by Ls plus 1 by Lc. So this is the expression of the current in this circuit we are going to get. So this is called as a characteristic equation. So this is called as a characteristic equation. The denominator part is called as a characteristic equation, which is S square plus 2 zeta omega ns plus omega n square. So this is the standard equation. So now we are going to compare the standard equation to this equation. So finally we are going to get omega n is equal to omega n square is equal to 1 by Lc. So therefore omega n is equal to 1 by under root over Lc, and 2 zeta omega n is equal to R by L. So we got that 2 zeta omega n is equal to R by L. So therefore zeta is equal to, if you substitute omega n is equal to 1 by under root over Lc, and if you do a simplification, we are going to get zeta is equal to R by 2 into under root over C by L. So zeta is going to lie between 0 to 1. So zeta value can lie only from 0 to 1. So therefore this is the range of the zeta. So now I want to make the zeta value less than 1. So I want to make the value of zeta less than 1. So what is the condition? At what condition we can make a zeta value less than 1? So therefore here when zeta is going to lie between 0 to 1, then only we are going to get a under damped response. Means the response is going to get under damped, means the oscillations are going to get reduced. So therefore here I am going to assume in this manner. So I want zeta less than 1. So zeta is equal to R by 2 omega nl less than 1. So R is less than 2 omega L. So here omega n is 1 by under root over Lc. So if you solve this one, if you substitute here, we are going to get finally R is less than 2 into under root over L by C. So if you do a square on the both sides, we are going to get R square is less than 4 into L by C. So R square is less than 4L by C. Means when R square is less than 4L by C, then we can say that we are going to get the value of zeta which is less than 1. Means the system is said to be under damped. Means we can say that the oscillations are going to get reduced. The oscillations are going to get reduced. So therefore the resonant frequency is equal to omega n into under root over 1 minus zeta square. So the resonant frequency is equal to omega n into under root over 1 minus zeta square, where omega n is called as a natural frequency. So as the current is going to get damped, so if you are going to give a DC source, the current is going to get damped in this manner. Let us assume that the latching current is 0. Let us assume that the latching current of thyristor is 0. So whenever the latching current is 0, means whenever the current is going to become 0 and it is trying to become negative after pi. So negative current connected passes to thyristor. So therefore we can say that the means the thyristor is going to get open after omega t is equal to pi. So after omega t is equal to pi, it is going to off. Or simply we can say we have assumed that the latching current is equal to 0 or the holding current is equal to 0. So we have assumed the holding current is equal to 0. So therefore here the I of t wants to try to become negative, but at pi it is going to become open because it wants to be negative. So the thyristor will be open. So simply we can say that as it is open, means we are forcefully with the help of RLC components, we are trying to make the circuit to be under damped. So therefore here we are going to get the circuit as, or you can say the switch as open. So we are going to finally make the thyristor as open. If IA is less than IH means whatever the current in the circuit is less than holding current, then SCR is off. I am going to assume the holding current is nearly equal to 0. So therefore, whenever the current wants to be negative, then definitely SCR is going to become off. So 0 to pi, only in this range the SCR is on. So therefore, omega RT is equal to pi. So that is the resonant frequency. So omega RT is equal to pi. So if you want to know what is the value of time t, so therefore t is equal to pi by omega r. So t is equal to pi by omega r. So omega r is equal to omega n into under root over 1 minus zeta square. So this is the time. Up to this time only the SCR is going to get conduct. So only up to this time the SCR is going to get conduct means we are forcefully making the thyristor current to be underdamped by choosing the value of RLC in such a way which is R square is less than 4L by C. So by this way we are going to make the current to be underdamped. So whenever the current is lesser than the holding current, then automatically thyristor is going to get open circuit or it is off condition. So therefore conduction time of SCR after this SCR gets torn off. So after this time the SCR is going to get torn off, or we can say this is the conduction time of SCR. After this SCR is going to get torn off. This is called as the class A commutation or the load commutation, means we are going to off the thyristor based on the values of the RLC. So based on the values of the load components which are the RLC, we are going to off this SCR. So that is the reason it is called as the class A commutation or the load commutation. Now we are going to learn the current commutation or the class B commutation. So current commutation or the class B commutation. So whereas class A commutation is also called as the load commutation, whereas the class B commutation is also called as the current commutation. So now here this is a circuit of this current commutation or the class B commutation. So here we are going to give a supply DC voltage of Vs and this is the load. So here there is a thyristor. Let me assume that this is called as the TM or simply main thyristor. So this we want to off by using an external circuit. So this another thyristor we are going to keep, this is called as an auxiliary thyristor, and this is a capacitor and this is the inductor. So now this is a diode. So this is the configuration of this auxiliary thyristor, capacitor, inductor and the diode. The current in the main thyristor is Im. The voltage across the capacitor is plus minus Vc and this is the inductor L, and let me assume this is the direction of the current IC and this is the load current I0. So we are going to make some assumptions in the circuit, which is I am going to assume that I0 is a constant value, means I am going to assume that the load current is always constant with respect to time, means I am going to assume that the load is having a huge value of inductance. So because of that its value of the current is very constant. And also I am going to assume that the initial value of the capacitor voltage, the initial value of the capacitor voltage is equal to source voltage, means initially the capacitor is having some voltage. Initially the capacitor is having some voltage which is equal to the supply voltage. So the initial voltage of the capacitor is equal to supply voltage itself, which is equal to Vs. And Tm is on when t less than 0. See, before the time less than 0 only the Tm is on. So by using some external circuit we should off the Tm. So Tm is on when time less than 0. So after t greater than 0, so by the help of the circuit arrangement we should turn off this thyristor. So now we are going to do the analysis of this circuit. See, mode 1. So there are 3 modes. So now we are going to study the starting mode, the mode 1. See, the mode 1 is simply here at t is equal to 0. At t is equal to 0 we are triggering TA is triggered. So at t is equal to 0 the auxiliary thyristor is triggered. The auxiliary thyristor TA is triggered. So therefore now if TA is triggered, what is going to happen? When TA is triggered, then you can say clearly here. So this is the circuit diagram you are going to get. When TA is triggered, so this is the circuit diagram we are going to get. So this is plus or minus Vc and this is L. So this is the LC circuit. So pure LC circuit. So the capacitor is going to discharge, or we can say the capacitor is going to transfer its electrical energy into magnetic energy in the inductor. So therefore this is the direction of the current. So from plus to minus means the current is going to flow in this direction. So therefore now I want to know what is the current here. This current will be, actually the current will flow in this direction, but we want the current in this one, which is reverse one. So therefore, the capacitor current IC of t is equal to minus ICP into sine omega t, where ICP is called as the Vs into under root over C by L, because this is the initial value of the capacitor voltage. So therefore, if you want to know what is the current, here? The capacitor current IC of t is equal to minus ICP into sine omega t, where ICP is equal to Vs into under root over C by L. And if you want to know what is the capacitor voltage, which is Vc of t is equal to Vs cos omega t. So Vs cos omega t is the capacitor voltage. So this is the capacitor voltage, and omega is called as the 1 by under root over LC. All these things we have already discussed. So this is the omega is equal to 1 by under root over LC. So therefore, we can see clearly the capacitor is going to have a voltage of Vs cos omega t. So IC of t is equal to minus ICB into sine omega t, whereas Vc of t is equal to Vs into cos omega t, whereas omega is equal to 1 by under root over LC. So based on this, now we are going to do the analysis of this circuit. So now I have already told you, I have assumed that the load current is always constant. So it is always constant with respect to time. So now we will draw the graphs of the capacitor current and also the capacitor voltage with respect to time. So the capacitor voltage is equal to, I have already told you in the mode 1, the capacitor voltage is equal to Vs cos omega t. So Vs cos omega t means, so this is the graph we are going to get. Up to 0 to pi. So up to 0 to pi, this is the graph we are going to get. And so you can see the current expression is minus Vs under root over C by L into sine omega t. So therefore minus means it will be, actual sine means positive, but minus means it will be negative in this direction. So this is the direction of the current you are going to get. See, after pi, the current wants to try to be positive. See, after pi, the IC want to be positive. If IC is positive, what is going to happen? If IC is positive means this current cannot enter into the auxiliary thyristor. So this current cannot enter into the auxiliary thyristor. So this IC cannot enter into auxiliary thyristor. So therefore, automatically this auxiliary thyristor is going to get turned off. So this auxiliary thyristor is going to get turned off now automatically at the end of the mode 1. So therefore, at the end of mode 1, the current wants to be positive. So therefore, this current cannot enter the TA. So therefore, this TA is going to get off automatically. So now this IC is going to flow through this diode. The diode is there now. From there, this current is going to get flow. So up to 0 to pi. As you can see clearly in that circuit, as the up to that time the diode is open. So up to that time the diode is open. So because of that, we can say that up to the time the diode is open. So therefore, whatever the main current is equal to, whatever the current in the main thyristor is equal to the load current. So therefore, I0 will be there up to, so the main, or we can say that the current in the main thyristor is equal to load current up to 0 to pi. This is called as the mode 1. So now we have analyzed the mode 1. So you can see clearly the maximum value of the current, which is flowing through the auxiliary thyristor is Vs into under root over C by L. So Vs into under root over C by L is the maximum value of the current, which is flowing through this auxiliary thyristor. So therefore, we can say that the maximum amount of current which is flowing through the auxiliary thyristor is ICP, which is Vs into under root over C by L. So Vs into under root over C by L is called as the maximum amount of current which is flowing through this auxiliary thyristor. So now we are going to study the mode 2. I have already told you at mode 2 the current IC want to be positive. So IC cannot enter the TA. So therefore TA will be open. At the end of mode 1, this TA is going to get open. So now this IC is going to flow through this diode. So now you can see clearly. So therefore this is already short circuit. Because it is always conducting. So therefore then IC of t will be same as the previous one, which is ICP into sine omega t, because it's a still LC circuit, because this is short circuit. So still IC of t will be still ICP into sine omega t. Whereas if you apply the KCL at this point, so this is IM and this is IC and this is I0. So IM plus IC is equal to I0, because sum of incoming currents is equal to outgoing current. So IM plus IC is equal to I0. So Im is equal to I naught minus Ic. Whereas I naught is a constant value because we have assumed that the load is having huge value of inductance. So its value is always constant. Whereas Ic is increasing. So as time increases, the Ic value increases. So when Ic value increases, this overall value decreases because this is constant and Ic is increasing. So therefore overall value decreases. So now we can say that the current in the main thyristor is now increasing in the mode 2. In the mode 2 region, we can say that the amount of current in the main thyristor is decreasing slowly. So therefore, when IC is equal to I naught, then what is going to become? When these both are equal, then Im is equal to 0. So Im is equal to 0, we are going to get when IC is equal to I naught. So when the capacitor current is going to reach the value of the load current, then we are going to get the current in the main thyristor is equal to 0. So when I am going to assume that the holding current is equal to 0. So this current is now becoming 0. So therefore this Tm is going to get off at the end of mode 2. So at the end of mode 1, Ta is off. At the end of mode 2, Tm is off. So therefore at the end of mode 1, the auxiliary thyristor is off. At the end of mode 2, the main thyristor is off. So Tm gets off at the end of mode 2. So you can see clearly in the mode 2 from pi you can see the mode 2 region. This is the mode 2 region. So here as IC is still ICP into sin omega t, so it want to be positive. So it is increasing. So IC increases, then Im is equal to I naught minus IC. It goes on decreases. So So therefore when IC of t is equal to I naught, then Im is equal to 0. So this is called as at this point we are going to get that at the end of mode 2, the main thyristor is going to get off. So the main thyristor is on from t is equal to 0 to up to this point. Whereas auxiliary thyristor is only on from, we can say only to 0 to pi range only. The auxiliary thyristor was on. So you can see clearly the auxiliary thyristor was on only in the range of mode 1 only. Whereas main thyristor is on up to mode 1 and also up to mode 2. So the combination of mode 1 and mode 2, the main thyristor was on. At the end of mode 1, the Ta was off. At the end of mode 2, Tm was off. So let me assume this is omega T1. Omega T1 is equal to pi. So this is overall range is called as the omega T1 and this is called as omega T2. So overall mode 1 range is called as omega T1 and overall mode 2 range is called as the omega T2. Still the capacitor voltage is same. So in the mode 2, still the capacitor voltage is same, which is Vc is equal to Vs cos omega t. So this is the mode 1 and this is the mode 2. Still it is equal to Vs cos omega t. So it will be increasing in this direction. So I already told you Im is equal to 0 at the end of mode 2. At this condition, the capacitor current is equal to the load current. So therefore I want to find what is this value. So therefore omega t is equal to pi plus omega t2 because it's a combination of mode 1 plus mode 2. At the end of mode 2, I want what is the value of overall angle. So omega t is equal to mode 1 plus mode 2. So pi plus omega t2. So at that point, I want to find what is the capacitor voltage also. So capacitor voltage, as you can see from the graph only, the capacitor voltage is always negative there. So therefore Vc of t is equal to minus VR we are going to consider. So now I have already told you the basic formula. In the mode 2 still it is same Vs cos omega t, whereas omega t is equal to pi plus omega t2 is equal to Vc value is now minus VR. So here cos of pi plus omega t2, so cos is again positive. So cos pi plus means it is basically, this is third coordinate. So the third coordinate, the cos is negative. So therefore minus cos omega t. So minus cancels. We are going to get Vr is equal to Vs cos omega t2. So therefore this is the value we are going to get. So now I want to find what is the value of the current at that point omega t2. So at this point omega t, I want to find what is the value of the current. So therefore ICP into sine of omega t2 is equal to I naught. See, still it is omega t only, whereas omega t is equal to pi plus omega t2. See, I have already told you the capacitor current. I have already told you the capacitor current here, it is still same, which is minus ICP sine omega t, where omega t is equal to omega pi plus omega t2 is equal to I naught. So sine of omega pi plus omega t2 is equal to minus sine omega t2, but there is also another minus. So minus into minus again positive. So finally we are going to get ICP into sine omega t2 is equal to I naught. So listen carefully. See, at omega t, the capacitor current is going to become I naught. So therefore minus ICP into sine minus ICP into sine omega t2 is equal to I naught. Whereas omega, then carefully again I am repeating here. See, minus ICP into sine omega t is equal to I naught. So therefore omega t is equal to pi plus omega t2. So therefore minus ICP into sine of pi plus omega t2 is equal to I naught. So sine of pi plus omega t2 is equal to minus sine. So again there is extra minus here. Minus into minus is positive. So finally we are going to get ICP into sine omega t2 is equal to I naught. So therefore omega t2 is equal to sine inverse of I naught by ICP. So t2 is equal to 1 by omega. So 1 by omega is under root over LC. So therefore under root over LC into sine inverse of I naught by ICP. So this is the time t2. So this is the time t2 at which it is going to having this much amount of value. So t2 is equal to here under root over LC into sine inverse of I naught by ICP. So if you want to find what is the value of the capacitor voltage at the end of mode 2, then we can say that already I have told you VR is equal to Vs cos omega t2. So VR is equal to Vs cos of, whereas omega t2 is equal to sine inverse of I naught by ICP. So this is the value of the capacitor voltage at the end of mode 2. So and also this is the time here. So this is the capacitor voltage at the end of mode 2. So VR is called as the voltage across the capacitor at the end of mode 2. This is the capacitor voltage at the end of mode 2. So this is the end of mode 2. So at the end of mode 1 TA was off. At the end of mode 2 TM is also off. So therefore now we are going to study the mode 3. So now we are going to study the mode 3 operation. So mode 3 is here. Now TA is also off. So TM is also off. As TM is off, what is going to happen basically? As TM is off, then whatever the capacitor current is equal to current in the load. So therefore whatever the capacitor current is the current in the load. So therefore simply we can say that IC will be always equal to I naught. So in the mode 3 always IC of t will be always equal to I naught. So therefore here, so therefore IM will be always equal to 0 in the mode 3 also. And also now we have to find what is the value of the capacitor voltage. I naught is a constant value. So if I naught is a constant value means simply this voltage drop across the inductor will be 0 because I naught is a constant. The current passing through inductor is a constant value. So therefore the voltage drop VL is equal to L into di by dt. As the current is a constant, so voltage drop across the voltage drop across the capacitor will be 0. I have already told you this is plus or minus Vc. So here plus or minus Vc means we are going to get negative value. We are going to get basically negative value at the end of mode 2. At the end of mode 2 we are going to get this value as negative means here simply we are going to get in this manner. See plus or minus Vc, this is plus and this is minus Vc. So negative means it will be minus plus. So this is a VR. So this much amount of voltage, is given as the reversed bias across the thyristor, main thyristor. So you can say circuit turn of time means the time for which the reverse bias voltage occurred when the main thyristor was off. So main thyristor was off after the mode 2. So after that time, for how much amount of time we are going to give the negative voltage across the main thyristor. So basically this main thyristor was on from omega t is equal to 0 to omega t is equal to pi plus omega t2. So the main thyristor was on from omega t is equal to 0 to omega t is equal to pi plus omega t2. So after up to this time it is doing the conduction. So and then in the watch time, in which time it is going to face the reverse voltage. So reverse voltage it is going to face for a circuit turn of time, which is here simply if you want to find what is the circuit turn of time, the time for which the main thyristor is going to face the reverse voltage, which is you go for the capacitor voltage, which is the I is equal to C dU by dt. So therefore so dVc of t is equal to 1 by C integration of IC of t into dt. So if you do that, if you go for the graph, then the capacitor voltage is changing from minus VR to 0. D into Vc of t is equal to 1 by C integration of 0 to Tc I of C dt. So if you do this one, we are going to get 0 plus VR is equal to I naught by, because capacitor current is equal to 0 is equal to I naught in this case. So therefore I naught by C into Tc. So therefore you are going to get Tc is equal to C into VR by I naught. So this is the call as a circuit turn of time for the main thyristor. So this is the circuit turn of time for the main thyristor. So this is the circuit turn of time for the main thyristor, means up to this much amount of time the capacitor is means up to this much amount of time the main thyristor is going to face the reverse voltage across it. So you can see clearly this is called as the capacitor or circuit turn of time. Up to this much amount of time the main thyristor is going to face the reverse voltage across it, which is from integration of minus VR to 0. So minus VR to 0 is equal to means integration of minus VR to 0 dVc of t is equal to 1 by c integration of t is equal to 0 to Tc I of t Ic of t into dt. So this is the way that you need to go for the integration. So finally we are going to get circuit turn of time is equal to C into VR by I naught. So therefore here integration of minus VR to 0 dVc of t is equal to 1 by c integration of 0 to Tc Ic into dt. So Ic into dt. So because Ic is equal to I naught, so from that we are going to get the we can say circuit turn of time is equal to C into VR by I naught. So this is called as the mode 3. So this is up to mode 2 and this is called as the overall mode 3. So now after this the capacitor voltage is positive. So capacitor voltage is positive. Positive means we can say simply that now Tm is going to face the forward block, means we can see it is going to now in the forward blocking mode, or simply it is already off. So therefore now only up to this much amount of time it is going to face the reverse voltage. After that it is going to get increase, and after that it is going to get increase, and finally it is going to become the same as the supply voltage. So the capacitor voltage is going to become the same as the supply voltage finally, because it is going to get charged. It is going to get charged. Whereas IC is always constant. It is equal to the load current itself all the time. Even in the mode 3 also it is same this one. So this is the mode 1, this is the mode 2, and this is the mode 3. So in all the mode 3 we can say that the capacitor current is always equal to I naught. So therefore, so in the mode 3 always the main resistor current is always equal to 0, whereas the load current is always constant. So finally the capacitor voltage is going to charge up to the supply voltage Vs. So now basically in the circuit, because of current only, the main resistor is going to get off. So because of current in the main resistor is decreasing. So because of current in the main resistor is going to become 0. So because of that only it is going to become off. So that is the reason it is called as a current commutation. So the main resistor was off because of main current is going to become 0. It is less than the holding current. So because of that only it is going to become off. So that is the result. It is also called as current commutation or the class B commutation. So the circuit turn off time for the main thyristor is the time for which the main thyristor is going to face the negative voltage across it, which is CVR by I naught. Where VR is called as the voltage across the capacitor at the end of mode 2. So now if you want to find what is the minimum current faced by the, so now here the main current, or we can say the current in the main thyristor, peak value is equal to I naught, that we can obtain in the graph itself, that we can see from the graph itself. So the peak value of the current in the main thyristor is equal to I naught, whereas circuit turn off time is equal to C into VR by I naught, and the peak value of the current in the auxiliary thyristor is equal to Vs into under root over C by L. So simply via IC of P. So peak value of the, it is also equal to the peak value of the capacitor current. The conduction time of TA. So TA is going to conduct only in the mode 1 region. In the mode 1 region only TA is going to conduct. So omega T1 is equal to pi. So T1 is equal to pi by omega, whereas omega is equal to 1 by under root over LC. So we are going to get pi into under root over LC. So this is the time for which the auxiliary thyristor is going to get conduct. Time required to turn off Tm after TA is on. So what is the time required to turn off Tm when the TA is already on? The time required to turn off Tm after TA is on. So basically Tm is going to off after the end of the mode 2. So T1 plus T2. T1 is the time of operation of the mode 1 and T2 is the operation of the time of operation of the mode 2. So T1 is equal to pi into under root over LC, whereas T2 is equal to under root over LC into sine inverse of I naught by ICP. These things I have already told you. So simply we can say that this is the time for which the mode 2 was operating, and this is the time for which the mode 1 was operating. So if you do summation of these two things, we are going to say that after this time the main thyristor was going to get off after the on of the auxiliary thyristor. So the time required to turn off Tm after the TA is on is equal to T1 plus T2, where T1 is the time of operation of mode 1 and T2 is the time of operation of mode 2. So T1 is equal to pi into under root over LC, T2 is equal to under root over LC into sine inverse of I naught by ICP, where ICP is equal to Vs into under root over C by L. Maximum time required to turn off Tm after TA is on is equal to the minimum time required to turn off TM after TA is on is equal to. So minimum time required. So here, suppose let me assume that I naught is small. As the I naught is small, see if the value of I naught decreases, what is going to happen? If the value of I naught decreases, then definitely the mode 2 operation time is also going to get decreased. So let me assume I naught is nearly very small. So definitely then the overall time of TM is nearly equal to T1, the mode 1 operation only. So as I naught decreases, then the mode 2 operation time is also decreases. So therefore the minimum time required to turn off TM after TA is on. So the minimum time to turn off TM after the on of TA is nearly equal to T1. So T1 is the, or simply we can say that if I naught is very small, means at the end of time T1 or at the end of mode 1, both the main thyristor and also the auxiliary thyristor are going to off at the same time. So when I naught is very small at the end of mode 1, then both the main thyristor and also the auxiliary thyristor are going to get off at the same time. This is the minimum time. The capacitor voltage at the end of mode 2, so this is called as a VR. So VR is equal to, if you want to know what is the exact voltage, I have already told you, which is Vs into cos omega t. So Vs into cos omega t, whereas omega t is equal to simply I have already told you, which is pi plus omega t2. So pi plus omega t2. So therefore simply we can say that the capacitor voltage is equal to Vc into Vs into cos omega t. So omega t is equal to pi plus omega t2. So cos of pi plus omega t2 is nothing but minus cos omega t2. So minus Vs into cos omega t2. Whereas omega t2 is equal to, I have already told you, sin inverse of I naught by ICP. So therefore, so cos of omega t2 is sin inverse of I naught by ICP. So this is the value of the capacitor voltage at the end of mode 2. See, if the peak value of the current in the capacitor, if it is greater than I naught, then only commutation occurs. Otherwise there is no commutation. So only when the peak value of the capacitor current is greater than the I naught, then only this commutation process occurs. Means we are going to turn off the main thyristor. So only when the current in the capacitor, the peak value is greater than I naught, then only commutation occurs. So ICP is nothing but Vs into under root over C by L. Then only we can say that we can off the main thyristor. So this is about some of the important concepts of the class B commutation or the current commutation. So up to now we have discussed about the class A commutation is also called as the load commutation, whereas the class B commutation is also called as the current commutation. But now we are going to discuss the another commutation which is called as the class A commutation. So class A commutation is also called as the impulse or the complementary commutation. So class A commutation is also called as the impulse or the complementary commutation. So in that there are two cases. So we are going to discuss each case individually. So the case one now we are going to discuss. So basically this is a circuit. So here these are the resistor R1 and R2 and this is the thyristor T1 and T2. So we are going to keep a capacitor in between them and the polarity of the capacitor is plus minus Vc of t and the current in the capacitor is Ic of t. This is the polarity we are going to consider. So we are going to assume that the initial capacitor voltage is Vs, which is equal to the supply voltage. So the initial voltage of the capacitor is equal to Vs, which is equal to supply voltage. And here T2 is equal to already on. So T2 is equal to already on and T1 is off. And the T1 is off at t less than 0. So we have assumed that T2 is already on and T1 is off at t less than 0. So at t less than 0, T2 is on and T1 is off. Our aim is to turn off T2. So our aim is to, the main agenda of the circuit is to turn off the T2. Yeah, see the whatever the assumption is, the initial capacitor voltage is equal to supply voltage and also here T2 is initially on and T1 is off. So by using the circuit we should try to off this T2. So our aim is to turn off this T2. So now on T1. So automatically T2 gets turned off. So open T2. See whenever you on the T1. So whenever you on the T1 then plus minus. So plus minus is going to occur here. So simply we can say that for thyristor T2 there is a reverse bias voltage. So whenever there is a reverse bias voltage across the thyristor T2, it is going to become automatically turn off. So therefore we can say that whenever you on the T1, at the instant of on the T1, a reverse voltage occur across the thyristor T2. So therefore the thyristor T2 is now going to automatically, it is going to become turn off. And let me assume the current in the R1 is IR1 and the current in the R2 is IR2 and this is the current in the thyristor 1. So thyristor current 1 is a summation of these two currents by KCL. So IT1 is equal to IR1 plus IR2, whereas ICT is equal to minus of IR2T. So both are opposite in direction. So IC of T is equal to minus I2R of T. So therefore IT1T is equal to, you can substitute here, IR2 is nothing but minus IC of T. If you substitute here, we are going to get IT1 is equal to IR1 minus IC1 ICT. So IT1 is equal to here IR1. So what is the value of IR1? So if you apply the KVL in this loop, it's a plus Vs minus R1 into IR1 is equal to 0. So we are going to get IR1 is equal to Vs by R1. So Vs by R1 minus IC of T. So this is the value of the thyristor current IT1, which is Vs by R1 minus IC of T. So this is the value of the current IT1. So by applying this theorem, which is, so we want to find what is the nature of the capacitor voltage. So capacitor voltage is equal to final value plus initial value minus final value into e to the power of minus t by 2. So final value plus initial value minus final value into e to the power of minus t by 2. So F I F plus minus e to the power of minus t by 2. So Vc of t is equal to final value plus initial value minus final value into e to the power of minus t by 2. So now I want to find what is the initial value across the capacitor voltage. As I have already told you, the initial value of the capacitor voltage is equal to Vs. That thing I have already given assumption. So now I want to find what is the final value of the capacitor voltage. So if you keep the circuit for steady state, the capacitor is going to get fully charged. So means it is a fully charged means final value, the current in the circuit in this branch is 0. So current will be 0. So here, if this is 0 means whatever the supply voltage, total voltage is going to drop across this one. So both are of opposite polarity. So therefore Vc of infinity is equal to minus Vs. So therefore Vc of infinity is equal to minus Vs. And if you want to find what is the R equivalent across this capacitor, so you have to remove this capacitor and you have to short circuit this voltage source and try to figure out the what is the overall resistance. So as it is a short circuit into R1 is both are parallel. So therefore it is overall short circuit. So 0 plus R2 is again R2. So therefore R equivalent is equal to R2. Equivalent resistance across the capacitor is equal to R2. So you know the value of Vc of infinity, you know Vc of 0, and you know tau is equal to R equivalent into C equivalent. So tau is equal to R equivalent is equal to R2 into C. So if you substitute here, finally we are going to get Vc of t is equal to minus Vs plus 2 Vs into e to the power of minus t by R2C. So this is the expression that we are going to get across the capacitor. See, now I want to find what is the maximum voltage across the thyristor T2. Maximum voltage I want to figure out. The maximum voltage across the thyristor T2 means the maximum reverse voltage that is applied across the thyristor T2 is equal to supply voltage itself. That is equal to supply voltage itself. If you substitute T is equal to 0, we are going to get this is 2 Vs minus Vs, which is Vs. So Vs is the, we can say that Vs is the maximum amount of reverse voltage that is kept across the thyristor T2. Time goes on, its value goes on decreases. As time goes on, its value goes on decreases. I know the value of the capacitor voltage. So now I want to find what is the capacitor current. So capacitor current is equal to C into dVc by dt. So you know the value of Vc of t, do the differentiation and multiply by C. Finally we are going to get minus 2 Vs by R2 into e to the power of minus t by R2C. And I already told you IT1 is equal to IR1 minus IC of t. IR1 is equal to Vs by R1 plus minus IC of t. So minus IC of t is 2 Vs by R2 into e to the power of minus t by R2C. So this is the expression of the overall thyristor current. And if you want to see, you can, this is a exponential decaying term. So the maximum amount of current which is passing through the thyristor T1 is called as the, if you substitute T is equal to 0, we are going to get Vs by R1 plus 2 Vs by R2. So this is the maximum amount of current which is passing through the thyristor T1. And if you want to know what is the maximum amount of reverse voltage appeared across the thyristor T2, which is equal to supply voltage itself. So now if you want to find what is the circuit turn off time for thyristor T2 means the time for which the reverse voltage appeared across the thyristor T2. So that is, let me assume this is TC2. So TC2 is the circuit turn off time for thyristor T2, which is the time for which the reverse voltage appeared across the thyristor T2. Because see, let me assume, see, already Vc of t is a negative, means it's like reverse polarity across the, it is a reverse polarity across the thyristor. So it is going to give you negative value, so it goes on decreases, so from negative value means it goes on increases in the positive direction, it is goes on increases, and finally it is going to become 0. After that it will be positive. So therefore if Vc of t is a negative, basically here Vc of t is initially positive, so from positive it goes on decreases in the negative direction because the final value is minus Vs. So initial value is plus Vs and the final value is minus Vs. So it is going from plus to minus. So whenever the Vc of t is positive, then only it can provide a negative bias or reverse bias to the thyristor T2. So whenever it is a negative, then it will be providing a forward blocking voltage. So we have to find at what time it is going to become 0. So therefore see that at t is equal to Tc2, the capacitor voltage is equal to 0. So we can substitute in the capacitor voltage expression Vc of t Vs into 2 into e to the power of minus t by r to c minus 1. So if you substitute Vc of t is equal to 0 at Tc, some circuit turn of time, you are going to get the expression of the circuit turn of time, which is R2 into C into ln2. So we can say that up to this much amount of time, the capacitor voltage is positive. If capacitor voltage is positive, means it is providing a reverse bias across the thyristor T2. So therefore that is the meaning of this one. So which is R2 into C into ln of 2. So R2 into C into ln of 2. Because of R2 only, means here thyristor T2 is provided across the R2 branch. So therefore you have to use the word R2 into C into ln2, because we are going to keep the thyristor T2 in the R2 branch. So because of that, circuit turn off time will be R2 into C into ln of 2. So up to this much amount of time, the capacitor voltage is positive, means it is decaying from plus to 0. Whenever it is a positive, then only it is going to provide a reverse voltage across the capacitor. So this is the circuit turn off time until which the reverse bias is occurring across the thyristor T2. So we can say that whenever we automatically turn on the T1, automatically T2 is going to turn off at that instant only. Now let me do the second case circuit. So here this is a circuit, this is second case circuit. So R1, R2, T1, T2, and this is the current in the R1, which is IR1, and the current in the R2 is IR2. And now just we interchange the polarity of the capacitor. Now this is plus minus Vc and this is the current IC. Just we interchange the polarity of the capacitor voltage and the polarity of the capacitor current. Only this thing we have interchanged. So now we are assuming that the initial capacitor voltage is equal to supply voltage itself, and initially now T1 is on. So now T1 is on and T2 is off. So initially T1 is on and T2 is off at t less than 0. So with the help of T2, now we should turn off the T1. In the previous case, with the help of T1, we turned off the T2, but now with the help of T2, we are going to turn off the T1. So therefore we can say that initially T1 is on and T2 is off at t less than 0. So with the help of T2, we should turn off the T1. So our main aim is of the circuit is to turn off the thyristor T1. So now on T2, so automatically T1 gets off, because if you on T2, then this plus minus, so this is going to act in this plus minus, means this thyristor is going to face a reverse voltage, so it is going to automatically becomes turn off. So therefore when you on T2, at that moment only a reverse voltage is across the T1, so therefore the T1 is going to get turned off. This is the circuit that you are going to get after turning on the T2, so T1 is going to get turned off. So this is IR1 and this is IR2, and this is the capacitor current IC, and this is the current in the thyristor, which is IT2. So now you can see clearly IC is opposite of the IR1, so IC of t is equal to minus IR1. And if you want to know what is the value of T2, which is summation of IR1 plus IR2, whereas IR1 is the negative of this one, so minus IC of t. And also IR2 is equal to, if you apply the KVL in this loop, we are going to get plus Vs minus IR2 into R2 is equal to 0. So IR2 is equal to Vs by R2. So therefore IR2 is equal to Vs by R2. So therefore you can substitute in this expression, we are going to get I22 is equal to, which is minus ICT plus Vs by R2. So therefore Vs by R2 plus, I want to find what is the value of the capacitor current. So after that we are going to get this expression. So let me find what is the capacitor voltage first. Already told you the capacitor voltage is equal to final value plus initial value minus final value into e to the power of minus t by 2. So final FIF plus minus e to the power of minus t by 2. So I want to find what is the value of the capacitor voltage I want to find. Already I have told you the initial value of the capacitor voltage is plus Vs and final value I want to figure out. If at final value the capacitor is going to get fully charged, so fully charged means current is equal to 0. So current in this branch is 0. So whatever the supply voltage is equal to voltage across this one. So both are of opposite nature. So therefore Vc is equal to minus Vs. And I want to find what is the equivalent resistance across this capacitor. So remove this capacitor and try to find what is the equivalent resistance across this capacitor. So short circuit this voltage source. So if you short circuit this one, this and R2 are in parallel. So overall short circuit is 0. So 0 plus R1 is R1. So therefore R equivalent is equal to R1. So tau is equal to R equivalent to C. So therefore R1 into C. So Vc of t is equal to, substitute the initial value and the final value in this expression, and tau is equal to R equivalent into C, which is R1 into C. So finally we are going to get this expression, which is minus Vs plus 2Vs into e to the power of minus t by R1C. So this is the amount of the capacitor voltage, and see this is the, and it's, see this is minus Vs. If you substitute t is equal to 0, we are going to get plus Vs. So therefore see the capacitor voltage is going from plus Vs to minus Vs. The capacitor voltage is going from plus Vs to minus Vs, means initial value is plus Vs and the minus and the final value is minus Vs, means it is going from positive to negative. So positive to negative. So what is the maximum value of the maximum value of the reverse voltage appeared across the thyristor T1. So when this is positive, then we can say here the capacitor is going to face the thyristor T1 is going to face a reverse voltage. So the maximum amount of reverse voltage appeared across the T1 is equal to supply voltage itself, or we can say the maximum value of the capacitor voltage is equal to Vs. So now if you want to find what is the value of the capacitor current, which is C into dVc by dt. So if you solve this one, if you do the differentiation and multiply by C, finally we are going to get this expression. So this is the value of this IC of t. But IT2 is equal to minus ICT plus Vs by R2. So you know the value of IC of t, substitute here, we are going to get finally Vs by R2 plus 2Vs by R1 into e to the power of minus t by R1C. So if you want to find what is the maximum value of the current passing through the thyristor T2, so substitute here t is equal to 0, we are going to get Vs by R2 plus 2Vs by R1, because it is a exponential decaying term. So it will be maximum only at t is equal to 0, whereas this is a constant term. So overall it will be maximum only at t is equal to 0. So this is the value of the maximum current flowing to the thyristor T2, which is equal to IT2 max, maximum amount of current passing through the thyristor T2. And if you want to find what is the maximum amount of reverse voltage appeared across the thyristor T1, which is equal to Vs. So if you want to find what is the circuit turnoff time of T1, circuit turnoff time means the time for which a reverse voltage appeared across the thyristor T1. So I already told you, when capacitor voltage is positive, then only it will be a reverse voltage across the thyristor T1. But if capacitor voltage is negative, means then it is not a reverse voltage across the capacitor. So only thing that we need to find, up to what time the capacitor voltage is positive. So it is decaying from plus Vs to 0. So in how much amount of time it is decaying from plus Vs to 0. So here Vc of t expression we have already know, which is minus Vs plus 2Vs into e to the power of minus t by R1C. So we have to find at what time its voltage is going to become 0. So only in this time only it is a positive. So if you substitute here at Tc1, its value is equal to 0. Then if you do simplification, finally we are going to get the time for which the reverse voltage appeared across the T1 is equal to R1C into ln of 2. So for this much amount of time, a reverse voltage appeared across the thyristor T1, which is R1 into C into ln of 2. So R1 into C into ln of 2, for this much amount of time, a reverse voltage was appeared across the thyristor T1. So if you want to find what is the circuit turnoff time for T1, which is R1 into C into ln2, if you want to find what is the circuit turnoff time for the thyristor T2, which is R2 into C into ln of 2. So note here, See, C we are going to get, which is Tc2 by R2 into Ln2. C is equal to Tc1 by R1 into Ln of 2. So you are going to get this both expressions. So therefore always choose the higher C. So out of these two expressions, which expression we are going to get the higher value of C, choose that value of C. The Tk is called as the SCR turn of time. Means you can say it is a device turn of time. The Tc is called as the circuit turn of time. So therefore TQ is called as the device turn of time or the SCR turn of time, whereas Tc is called as the circuit turn of time. So always we have to use only the circuit turn of time in these problems. So therefore the safety factor is the ratio of the circuit turn of time by the device turn of time, because always circuit turn of time is always greater than the device turn of time. So always the circuit turn of time is always greater than the device turn of time. So therefore the safety factor is equal to Tc by Tq. So therefore Tc is equal to safety factor into Tq. So always SF is greater than 1 because it is a ratio of circuit turn of time by the device turn of time. So therefore Tc by Tq. So Tc is always greater than the Tq. So when R1 is equal to R2, if suppose R1 is equal to R2, both are going to have the, if R1 is equal to R2 means both are going to give you same expressions, means both the thermistors are going to have a same amount of circuit turn of time. When R1 is equal to R2, then both thermistors are going to have the same of the circuit turn of time, which is C is equal to Tc by R into Ln of 2, where SF is called as the safety factor. Called as the complementary or class C computation. So complementary or impulse means because of one thyristor we are going to turn off the other thyristor. So this is this way is called as the complementary or impulse, or simply we can say it is a class C computation. So now we are going to discuss the last concept in this lecture, which is the class D computation or the voltage computation. So class D computation is also called as the voltage computation. So I have already told you class A is also called as the load computation, whereas the class B is also called as the current computation, and the class D computation is also called as the complementary or the impulse computation, whereas the class D computation is also called as the voltage computation. This is the circuit diagram. So this is the circuit diagram for this class D computation. So basically here there is a source of DC source of Vs and there is a load with a voltage of output voltage of V0 and the output current is I0, and there is a freewheeling diode we are going to keep across the load. So this is the main thyristor that we need to off. So here we are going to keep an inductor and a diode in this fashion and a capacitor. In the previous case, in the class B, there is a capacitor, inductor and diode in this format. But here we are going to reverse the direction and we have to keep in this manner. So whatever the capacitor is there here, we have to move it upward. So this is called as the just you have to go for some amount of arrangement. So this is the capacitor, auxiliary thyristor, inductor, and the we can say this is the diode. So with this combination, we are trying to make the TM to get off. So with the help of this circuit, we are going to make this TM as off. So the current in the main thyristor, I am going to assume which is ITM is the current in the main thyristor, and IC is the capacitor current in this direction. So IC is the current in this capacitor. So based on this, we are going to analyze, and ID is called as the diode current. So based on this, we are going to analyze. So before that, let me take some assumptions, which are the capacitor initial voltage is equal to supply voltage. So the capacitor initial voltage is equal to supply voltage, and I0, the load current, is constant. So these are the two assumptions that I am going to consider. The initial capacitor voltage is equal to supply voltage and the load current is always constant with respect to time. So with these two assumptions, now we are going to analyze this circuit. So here now we are going to discuss the mode 1 operation. Mode 1 means up to omega t is equal to pi. Up to omega t is equal to pi is called as the mode 1 operation. See, now already main thyristor is on, so therefore now the auxiliary thyristor is off. In this case means you are not offing, means we are not owning the auxiliary thyristor. So therefore what is going to happen, as the TM is on, so therefore there is a capacitor, there is an inductor, and the current is going to flow in this direction. So diode is also conducting. So therefore TM is on and the TM is on and TI is on during this whole mode 1 operation. So this is basically a LC circuit. So therefore IC of t is equal to, Vs into under root over C by L into sin omega naught t. So this is the value of the current. So therefore IC of t is equal to, Vs into under root over C by L into sin omega naught t, where omega naught is equal to 1 by under root over LC. So this is the value of the capacitor current, which is equal to Vs into under root over C by L into sine of omega naught t, where omega naught is equal to 1 by under root over LC. So if you want to know what is the value of the capacitor voltage, which is Vs into cos omega naught t, where omega naught is equal to 1 by under root over LC. So here this is the capacitor current, means IC is upward, so therefore it is downward. So if you apply the KCL at this point, the thyristor current is a summation of the capacitor current plus the load current. So therefore thyristor current is equal to summation of the capacitor current plus the load current I naught. And always V naught, if you apply the KVL in this loop, we are going to get the output voltage is equal to source voltage. So therefore V naught is equal to Vs. So now we are going to draw the graphs for this period of omega t is equal to pi. I have already told that the load current is always constant with respect to time, and the load current is equal to I naught. Because of highly inductive load, the current is always constant with respect to time. And the capacitor current is equal to Vs into under root over C by L sin omega naught t. So from 0 to pi it is going to have a positive value. So this is the value of the current IC of t, which is Vs into under root over C by L into sin omega naught t in the mod 1 range of 0 to pi. Whereas the capacitor voltage is equal to, so the capacitor voltage is equal to, or simply we can say this is called as the current in the main thyristor. So current in the main thyristor is summation of I naught plus IC of t. So this is base is I naught. So on this we have to draw this graph. On the base, on the above we have to draw this capacitor current. So it will be like this one. So up to here. So if you want to draw the capacitor voltage up to 0 to pi, which is Vs cos omega naught t, so you are going to get in this format. So from 0 to pi we are going to get Vc in this format, whereas the load voltage is equal to Vs up to 0 to pi. So 0 to pi is called as the mode 1 operation. So now we are going to discuss the mode 2 operation. So the mode 2 operation is, say at omega t is equal, means from omega t2 to omega t. So from omega t2 to some omega into capital T. So this is what we are going to analyze. Means simply we can say that from omega t2 to omega t we are going to go for the mode 2 operation. Mode 2 operation. This starts at t2. This starts at t2 and now we on ta at t2. So basically this process is going to start at time t2 and now we are going to on ta. So now we are going to on ta at t2. So at t2 instant we are going to turn on the ta, the auxiliary thyristor. See, when IC wants to become negative, when IC wants to be negative, it indicates that when IC is negative means it is going against that diode. So it is going against the diode means the diode is going to now become open circuit. When the diode is open circuit means simply IC is equal to 0. So IC is equal to 0. So the diode is open. Similarly, if IC is equal to 0, whatever the ITM is equal to I naught. So therefore whatever ITM is equal to I naught. So therefore the current in the main thyristor is equal to load current up to this point. This point is called as T2. So up to this time it is going to always be a same value. So therefore up to T2 its ITM value is equal to I naught. So therefore capacitor cannot change its voltage instantaneously. So therefore here see basically we are open circuit the freewheeling diode. So whenever it is a freewheeling diode it is open. So therefore only source, main thyristor and the load are connecting and remaining everything is off. So the capacitor voltage will be same as the previous case up to T2 point. Up to T2 means up to pi to omega T2 it will be same as the same supply, or the voltage will never change at the capacitor. So it will be same like this one. Similarly V naught is equal to, say as the Tm is on, so therefore V naught is equal to Vs here also. So up to here. So therefore we can say that this is not a mode 1 or mode 2. This is just a normal thing. So therefore up to this point Tm is on. So up to this point Tm is on. So up to this point we can say that Tm is on. So now at omega T2 we are going to on the auxiliary thyristor. We are going to on the auxiliary thyristor. So whenever we are on the auxiliary thyristor, what is going to happen? Definitely the capacitor voltage is going to occur across the main thyristor. So just at that moment the capacitor voltage is going to act across the main thyristor. So because of that already the capacitor voltage is negative. So the capacitor voltage is negative at this point means it is going to act like a reverse voltage across the main thyristor. So automatically the main thyristor is now going to get turned off. The moment you turn on the TA, the main auxiliary thyristor, the Tm is going to get turned off. So Tm is turned on only from 0 to Tt. 0 to T2. After that it is turn off. Whereas TA, at the moment we turn on the TA, at the same instant the TM is going to get turned off. So this starts at T2. Now we on TA at T2, so TM is going to off automatically. So you can see clearly, already I told you that capacitor voltage at end of T2, it will be the negative value. So therefore it is going to act like a reverse bias across the thyristor. So it is going to become turn off. So it is become turn off. So now we need to analyze this circuit. So if you apply the KVL in this loop, which is plus Vs, this is plus minus Vc of t. So minus Vc of t. So this is plus and this is minus Vc of t. So minus Vc of t and this is minus V0 is equal to 0. So finally we are going to get Vs minus Vc of t is equal to V0. So Vc of t is equal to Vs minus V0. So this is the capacitor voltage is equal to source voltage minus load voltage. So therefore Vs minus V0. So here now this is the capacitor voltage we are going to get in the mode 2 region. Whereas IC of t, so IC of t both are opposite, so therefore IC of t is equal to minus I0, whereas the main thyristor current is equal to 0 at the end of mode 1, or simply this is the circuit we are going to get at the end of mode 1. So simply we can say that this is the mode 2, the equations which are IC of t is equal to minus I0 and ITM is equal to 0 and Vc of t is equal to Vs minus V0. So based on this we are going to draw the graph for the mode 2 operation. So now you can see clearly in the mode 2 operation starts at T2. So from T2 we can see clearly IC of t is equal to minus I0. So it is minus I0. Whereas ITM is equal to 0. From mode 2 it is going to become 0. It is going to become 0. So you can see clearly in this diagram. Whereas Vc, so now capacitor voltage is going to get increase exponentially because simply the current in the capacitor is DC value. So therefore I is equal to C du by dt. So therefore Vc of t is equal to 1 by C integration of I dt. So I is a constant value. So it is going to increase in a straight line, like a ramp manner. It is going to get increase. So it is going to increase until the capacitor voltage is equal to supply voltage only. So it is going to increase until the voltage across the capacitor is equal to source voltage. So in the mode 2, the output voltage is equal to Vs minus Vc of t. So Vs minus Vc of t. So you can see clearly here Vs minus Vc of t. At T2 the capacitor voltage is minus Vs. So Vs minus Vc of t means Vs minus of minus Vs, which is 2Vs. So 2Vs we are going to get, and as the capacitor voltage increases, so you can see clearly the capacitor voltage is increasing. As the capacitor voltage increases slowly, then we can say that the output voltage goes on decreases. So as the capacitor voltage increases, then simply we can say that this value goes on decreases. So this value is the output voltage goes on decreases. So it is going decreases. So finally when Vc of t is equal to Vs, so therefore V0 is equal to Vs minus Vs, which is equal to 0, because V0 is equal to Vs minus Vc of t. So therefore if Vc of t is equal to Vs, so therefore the output voltage is equal to 0. So you are going to get the output voltage as 0. So therefore at the end of mode 2 the voltage across the load is equal to 0 you are going to get. So this is the 0 voltage we are going to get at the end of mode 2 at the output voltage. So you can see clearly this is called as a circuit turn off time, means the time for which a reverse voltage or negative voltage appeared across the capacitor. So appeared across the main thyristor. So main thyristor was on from 0 to T2. Only at this instant it is became off. So the time for which a reverse voltage appeared across the main thyristor is from minus Vs to 0. So this much amount of time here it is going to appear a negative voltage across the main thyristor. So this is called as the circuit turn off time. So this is both are equal. So here as it is a straight line, so whatever the time from minus Vs to 0 is equal to time from 0 to Vs. So overall value is 2 cm. So this is TCM and this is TCM. So the overall time for mode 2 operation is 2 times the circuit turn off time. So Tm is going to on from 0 to T2 at the moment Ta is on by me. So Ta we are going to on by me. At that instant Tm is going to get turn off and Ta is going to conduct only from this mode 2 operation. Means only in the mode 2 this Ta is going to conduct. After the mode 2 ending, the Ta is going to get turn off automatically. So if you want to know what is the maximum amount of current in the main thyristor, which is equal to I naught plus, which is equal to I naught plus Vs into under root over C by L. This we can get from the graph itself. So I naught plus Vs into under root over C by L is the maximum amount of current in the main thyristor, and I naught is equal to Vs by R, which is equal to means output voltage is equal to source voltage when the main thyristor was on. So therefore I naught is equal to V naught by R is equal to Vs by R. So when the load is purely resistive load. And what is the maximum value of the current in the auxiliary thyristor? The maximum amount of current in the auxiliary thyristor is equal to the current in the load only. See, whenever the TA is on, Tm is going to get off automatically. So therefore, whatever the current in the main auxiliary thyristor is the current which is flowing in the load. So simply we can say that when TA is on, Tm is off. So whatever the current in the auxiliary thyristor is equal to current in the load. So therefore its peak value is equal to I naught. And minimum on time of Tm. So minimum on time of Tm is, see what is the time for which minimum we can on the Tm. So Tm can earn, the minimum time is omega T1 is equal to pi. Only up to this is called as a minimum, the minimum time for which that the main thyristor is on. So this is the minimum time for which the main thyristor is on, which is omega T1 is equal to pi. So therefore T1 is equal to pi by omega, where omega is equal to 1 by under root over LC. So we are going to get T1 is equal to pi into under root over LC. So this is the time for which, the minimum time for which the main thyristor was on. So now I want to find what is the circuit turn off time, the time for which the reverse voltage appeared across the capacitor or across the main thyristor. So which is, I have already told you the capacitor formula, which is dVc of t is equal to 1 by c integration of Ic of t into dt. In this period, in the circuit turn off time, the current to the capacitor is equal to load current, so I naught. So if you do this one, 1 by c integration of 0 to Tcm, and the capacitor voltage is changing from minus Vs to 0. So minus Vs to 0 it is changing. So therefore, if you do the simplification, we are going to get, say 0 minus of minus Vs is equal to 1 by c here into I naught into Tcm. So if you solve this one, we are going to get Tcm is equal to Cvs by I naught. So Cvs by I naught is the circuit turn off time for which the main thyristor is going to face a reverse voltage or the negative voltage across it. So if you want to know what is the conduction time of auxiliary thyristor, the conduction time of auxiliary thyristor is nothing but it is the mode 2 region. So the time for which the mode 2 is going to present, so for that time only the auxiliary thyristor is going to get conduct. It is 2 times of circuit turn off time, which is 2 into Cvs by I naught. So this is the time for which the auxiliary thyristor is going to get it is on in position. And if you want to find what is the average value of the output voltage, it is Vs into T on. See, I am going to assume T2 is equal to T on. I am going to assume T2 is equal to T on. So here T2 is equal to T on. So therefore V naught average is equal to Vs into T2. So T2 I am going to assume which is T on plus, so this area of this one is half into 2Vs into capital T minus T on by overall time is capital T. So therefore Vs into T on plus here half into 2Vs into capital T, or we can say it is 2 times of Tcm. So therefore here simply, so this overall mode 2 is nothing but 2Cm. So 2 into 2 Tcm. Vs into T on plus half into 2Vs into 2Cm by capital T. So if you solve this one, we are going to get Vs into T on plus 2 Tcm by T. So this I am going to assume this as the D effective. So this is called as the duty effective, or we can say effective duty cycle. So effective duty cycle. So V naught average is equal to some D effective into Vs. Where D effective is equal to T on plus 2 into Tcm by capital T. So therefore we can say where capital T. So capital T is nothing but the capital T is a summation of. So therefore we are going to get Vs into T on plus 2 Tcm by capital T. So this we are going to call it as the effective duty ratio. So this is called as the effective duty cycle or the effective duty ratio. Because of capacitor voltage, the Tm is off, so it is called as voltage commutation. So because of the capacitor reverse voltage only, the main thyristor was on. See, at the moment you are owning the auxiliary thyristor, so it is going to apply reverse voltage. So because of this reverse voltage only, this main thyristor was on off, so it is called as a voltage commutation. So because of capacitor voltage, the main thyristor is off, so it is called as the voltage commutation. And if you want to know what is the peak inverse voltage of freewheeling diode, so the voltage across the freewheeling diode is equal to voltage across the load. So the maximum amount of voltage is 2 Vs. So the maximum amount of voltage, output voltage is 2 Vs. So therefore the peak inverse voltage across the freewheeling diode is equal to 2 Vs. And the maximum current through capacitor, and the maximum current through capacitor is equal to, see, whatever the current which is flowing in the capacitor is equal to, which is the peak value of the capacitor current only. So therefore Vs into under root over C by L. So maximum current which is flowing through the capacitor is equal to Vs into under root over C by L. I am going to assume that I naught is lesser than the Vs into under root over C by L. Then only this is possible. So therefore here I have already assumed that the load current is lesser than the Vs into under root over C by L. So therefore this is the maximum amount of current which is flowing through the capacitor. So minimum effective on time for main thyristor. So what is the minimum turn on time, or you can say the minimum time for which the main thyristor was on, which is equal to I have already told you here, simply T1. So this is pi into under root over LC plus 2 VCS by I naught, or simply we can say that minimum effective on time for main thyristor is equal to pi into under root over LC plus 2 CVS by I naught. If they are asking like this, minimum effective on time for main thyristor means we have to go for the addition of these two things, which is pi into under root over LC plus mode 1 plus mode 2 time. So minimum mode 1 time plus minimum mode 2 time. So this is mode 1 time and this is the mode 2 time. So therefore we have to go for the addition of the mode 1 time and mode 2 time, which is pi into under root over LC plus 2 CVS by I naught. And if you want to know what is the maximum current which is flowing through the diode, the maximum current which is flowing through the diode is equal to the maximum amount of capacitor current, which is Vs into under root over C by L. So if you want to know what is the value of the average output voltage, so if you want to know what is the average output voltage, I have already told you the average output voltage is equal to, just now we have discussed, which is Vs into T on plus 2 Cm by T. So just now we have discussed the average output voltage is Vs into T on plus 2 Tcm by capital T. So 1 by capital T means frequency f. So this will be minimum only when T on is minimum. So only when the T on is minimum only the average value will become minimum. So minimum average output voltage we are going to get when this T on is going to become minimum. So this is called as a minimum time, where f is called as the frequency of switching main thyristor, where f is called as the frequency of switching main thyristor. So f is called as the frequency of switching main thyristor, and T on minimum is nothing but which is the time for operation of the mode 1, which is pi into under root over LC. And if you want to know what is the maximum output voltage, which is 2 into Vs. So these are the some of the important concepts of this lecture 2 in a very detailed manner. So we have discussed in detail about the rectifiers in a very detailed manner. And if you like the content of our channel, then please do like, share and subscribe our YouTube channel, and don't forget to press the bell icon button. So whenever we upload a new video, the direct notification comes to our mobile. If any information needed in our video lectures, then please do come in the comment section. We will definitely include all those information in the coming lectures. Thank you so much for watching this lecture. Peaceful and take care, and bye bye.